So yeah, my name is Dan Kuhl, and I lead the engineering team that's responsible for the Enterprise Design Group. The Enterprise Design Group is composed of a design team in Minnesota and in Longmont, Colorado. And really what we're focused on entirely is producing hard drive devices for the enterprise systems in the enterprise world. So my team is split between the two sites. So I brought a lovely sight of the mountains here that remind us of the Longmont. I did not bring the ice shanty view of Minnesota. So I'm here to talk about maybe three main things relative to hard drive and the technology and the innovation that goes inside the devices. And I really want to focus on capacity and focus on performance. Those are really probably two attributes you guys are worried about. There are a number of different attributes we worry about relative to how we deploy the devices, the manageability of those. I didn't have enough time to go into all those things, but really focus here on capacity and performance. And then specifically talk to the HPC purpose-built hard drive. So that device that's really, as Ken said, we focus completely on delivering that for the HPC market. So maybe a little segue into it though is just how does the hard drive work? So those of you that haven't seen the inside of the device, this is what it looks like. We've got really a recording head that flies at the end of a suspension, at the end of an actuator. That head is got a writer and a reader. It is really what takes the energy, creates the magnetic fields or reads the magnetic fields up and does that at some 100 nanometer track widths and data rates that are really approaching 2.5 gigabits per second. The tracking device there is a high-speed nanometer precision device. So really our control systems are state-of-the-art inside this device. On the back, there are high-powered data channels. So the electronics are purposely designed in order to decode that magnetic field, take those analog signals, convert them into digital signals, do all the error correction, and do that real time. And then the media itself, where the magnetic information is stored, where the data is stored, really is key. Some 10 nanometer magnetic particles get sputtered onto either an aluminum or glass disk, and those will just then spin up to 15,000 RPM inside of this device. And they do it for the life of their useful life, which can range upwards of 5 to 7 years. So pretty incredible bit of engineering. All that goes into these devices. So maybe think a little bit about the industry itself and the exabyte shipped. So we've seen a number of graphs today, and this one's just giving you a view of, look, the growth over the last 10 years has been pretty incredible on the number of exabytes shipped. So it really places a demand on all the market segments. In this case, we've got branded client as well as the enterprise demand, and a lot of growth in the enterprise specifically. And really what that focuses us to do is really then deliver the capacity points that the industry needs. And here we see really a chart that shows a representation of capacity points that we've shipped, that we've delivered in the industry over the few years, as well as what the projections are going to be as those start to go. And again, it's an exponential scale. We continue to see growth in both areal density as well as growth in the capacities that we ship to the industry. But there's challenges there. And really, these are probably three of the main challenges we deal with every single day. Thermal stability. So these magnetic particles are very small. Basically, to increase the density, we need to make them smaller and smaller yet. But what that does is as those grains get smaller, those grains of magnetic media, they become unstable. They're basically thermally unstable. They can, with a little bit of heat or just even time, they can switch, and then you'll lose the data. But solutions relative to the recording solutions are, we can then use solutions such as HAMR, such as BPM, or even combine those two together relative to heated dot magnetic recording, and really try to manage that migration as we go forward. And we'll talk a little bit more specifically around those technologies. The writer reader and the head media spacing scalability. So really these are the structures that we build inside that tiny little head. These things are continue to scale as we decrease track pitch. So that's the number of tracks that we can do per inch, as well as the bits per inch. So how much bits we can actually put into a linear density device. A couple of things that we've done is talk about shingled magnetic recording. We've also got two-dimensional magnetic recording, and then also just continuing our engineering relative to the head spacing, looking at new coatings, looking at new materials, looking at basically clearance algorithms as we manage that clearance between the head and the disk actively throughout the life of the drive. And then the other challenges really are the fixed format. we've got a limited amount of space that we can do. We don't have an infinite amount of space that we can go extend to continue to put heads and disks inside. We can obviously scale that up to a point, but we want to continue to do that. We want to continue to deliver more disks. That's an efficient way to add capacity into the device. And one of the things it does enable us to do is helium. Helium allows us to take that windage, if you will, the atmospheric excitation that goes on when you start to spin a disk at 7,000 or 15,000 RPM. Helium is one of those new things that can allow us to try and reduce that energy, reduce the power that's needed to turn these drives over. And as well as new form factors. We are looking at partnering with folks to look at maybe new and exciting form factors is what can we do to help scale the capacity growth. And we're not alone in the technology challenges. Seagate participates in this industry consortium, ASTC, and with essentially all of the hard disk drive suppliers as well as the supply chain that we use, get together and really debate and determine this roadmap going forward relative to what technologies, what type of growth we'll see and when we'll see them. And really this comes out of that consortium is looking at as we migrate from pure perpendicular recording up through HAMR, through BPM, and then a combination of the two with heated dot. This is really showing a progression of technologies that will continue to drive the technologies forward and the capacity forward. So maybe just to once again talk about specifically those technologies that we're working on and when we think is going to come out relative to our roadmap on the device side. So shingled magnetic recording is shipping today. And think of shingled as essentially what you do with your roof, right? The shingles themselves are very strong, rather large devices, but they get layered on top of each other to the point that only a little bit of it's exposed. We use the same technology inside the hard drive where we'll use a wider writer, we'll use something that's very robust in order to get the magnetic transitions down onto the media. We'll then overlap those, if you will, such that we can guarantee the stability, if you will, of the magnetic transitions, but still then scale the densities up. Helium, as I said, again, helium is an interesting a topic. It's actually, we seal the drives and then inject the helium into it. And what this does is really allow for management of that internal environment within the drive. I mean, the drives can spin, like I said, up to 7,000 to 15,000 RPM. They do create airflow dynamics inside there. Those are all well modeled within the engineering community. The helium allows us to reduce the amount of excitation both to the actuator itself and the suspension as well as the excitation to the disks. And what that does is allow you to increase the capacity, increase the density, reduce that noise, if you will, in the system. And then also by managing the power, we're able to then go ahead and put additional disk inside of the hard drive. And that helps with the capacity point. So on two fronts, it really helps with driving the capacity up. Two-dimensional magnetic recording. Historically, we've only worried about the downtrack signal, if you will. We write the data once and we come back and read it. And then we go to the next track, one track over. Well, there's dead space in between. And historically, we've not really worried about that. We've tried to minimize it. Two-dimensional magnetic recording is really, we're worried always about the downtrack, but we're also now cross-track as well. So we've got an extra reader in there. The design will basically use that information to help with the signal-to-noise processing that's done in the channel, and again, extend the capacity, extend the areal density of the device. HAMR is a heat-assisted magnetic recording. So HAMR, what it does is we actually take and we do apply heat to the media. Those small little magnetic particles, we can design them in two ways. Typically, they've got to be writable and they've got to be stable. And it's got to be done at a signal operating point. What a heat-assisted technology does is allow us to modify the operating point of the magnetic particles. We can apply heat, increase its temperature. It'll have a certain property at one temperature, which is basically fairly easy to write. Remove the heat, now the device becomes very stable. So it won't change over time. So again, HAMR is that next generation technology to allow us, again, to increase the capacity. BPM and with HAMR, which is now heated dot magnetic recording, is really taking that to the next level where we'll define islands, if you will, within the media that are separated physically. And what that does is the grain size, rather than being a random distribution, it's now an ordered distribution. And by doing that, we'll be able to, again, extend the recording technologies even further. On the performance side of that, so maybe shifting gears just a little bit and talk about some of the key enablers and the technologies being developed for performance improvement. Caching technologies. So one of the things within the disk drive, at least for the last 15 years to 20 years, has been we've had a cache inside the drive. We've always used DRAM. We've had that ability to look at the data as it comes into us, look at the data I/O as it comes out of us, and say, what do we want to keep within our cache, and pass that along. Certainly today, we've got a lot more options than we had maybe 15 years ago. With the advent of the flash technologies, this is driving a lot of innovation in our ability to manage the caching. Kinetic is our answer for object storage. So this is, again, rather than doing file or block level I/O to the device, go read block 17 and give me 32 of them, we'll say, please go put this object inside the storage. And this technology is really helps to allow, if the applications are able to really take advantage of some of the parallelism that's involved. Optimizing our drives for the subsystem. So this gets into maybe a little bit of the power discussion that maybe some of the folks are having issues with. But what we're really looking at is taking our drives and optimizing them specifically for the applications that we're seeing in enterprise, especially in enterprise stuff. Lower power, more efficient power, cooling, as opposed to performance. Those are all trade-offs that we can make in the devices that we offer and bring those to market. Parallelism as well. This is another exciting technology along with HAMR. Parallelism basically says, hey, look, I can manage two streams of information all at the same time. In some cases, basically, they'll allow us to double the data rate, if you will. We've seen a big progression here with the HPC drive that we'll get to in a minute, but parallelism is, again, another attribute that we can go and invest in. And then the enhanced processing drives. And this technology is really all about taking a compute element, put it down closer to your data. Rather than moving data up into your compute, take the compute device and put it down into the data device and really eliminate any transfer of data, eliminate that energy that you would have to move data back and forth, but do the compute where the data resides. Our caching strategy, we really look at it on two attributes here. One is on the read performance, and the other one's on write performance acceleration. Those are the two types of data streams we get. The raw drive performance you can see there, but we move up and to the right is what we really want to get to. We've got non-volatile caching, we've got enhanced write protection, we've got advanced caching algorithms, and then we've got the turbo boost, which is really our ability to take NAND flash, use a small bit of that, and then increase the read performance. And then the future being, how can I continue to invent and drive that performance up and to the right so that for all workloads, the caching becomes stronger. And one of the ways to look at that is really making sure we're watching where non-volatile memory is going. So we've got the hard drive there. We know it's a rotating magnetic storage device that has a mechanical actuator. We have done things already which will minimize the movement of that actuator, but still that gets us the lowest dollars per gigabyte that you'll see. You get up into DRAM where we've got DRAM on our drive that manages a lot of the high-speed traffic. But NAND with an HDD will provide us that ability to maybe provide an improved performance, but it's still manageable costs that are closer to the hard drive. And that's where a turbo boost comes in, right? Is we'll really take that small amount of NAND flash, we'll embed it in with the hard drive. Our firmware will manage the data flow, if you will, and we've got the ability to do that. In this case, we've got drives that will span the spectrum here from archive all the way up into the cache. And the hard drives play a big portion of that, but really trying to manage the data and manage the cache there. So HPC drive, so what is it? So we saw the insights here a little bit earlier about what a hard drive looks like. If we look specifically around a high-performance compute drive, what would we do differently? And it's really the heads. The heads are purposely built. What we wanted there is the highest data rate. And so what you need is fast transition times. We got to generate a magnetic field really quickly. That's got to get stored on the media. And we got to react to a reader that can read those back. The data channel itself has got to be designed and really focused on the ability to read that data back at those high data rates. The tracking solution that we put in here, it's a very stiff actuator. It's able to be very, very precise and fast move times. And then really around the disk, right? It came to fundamentally optimizing the form factor of the disk. making sure that we maximize the linear velocity, if you will, of what that disk can do, at the same time minimizing the power consumption and not losing too much from a signal to noise ratio. And really, these disks spin now at 10,000 RPM. It's really purpose-built to try and minimize the tracking errors and be able to hit the high data rates that really bring value to this product. So what do we end up getting out of it? Well, really 4 major things. Performance leadership, really as we look at both write performance and read performance and sequential data rate. The capacity that we want is a 4 terabyte capacity point here, the reliability and the power efficiency. And really, if you look at the performance, one of the things that we're really proud of, and I think you see the data in the Ken's subsystem data, is really the sequential data rate here is not only faster than other 7,200 RPM nearline drives that we would normally find in this environment, but actually the sequential data rate's faster than our 15,000 RPM drives. Our 15K drives typically will end up in a random mode where it's very maybe not focused on sequential workload, but focused on random workloads. This drive does outperform in the sequential workloads, so we're really proud of that. And then if you look at this normalized to performance per terabytes, you actually get some very impressive gains over a 7,200 RPM drive. Again, 2, 3, even up to 10x performance improvements. These are pretty good performance data. And then maybe just a little bit of look at where it's at. This is kind of the spec sheet for it, a high-level view of the 4 terabyte, 10,000 RPM. It's 5 disks, 3.5-inch form factor hard drive. Performance improvements across the board, better than our traditional 7,200 RPM drive, but still meeting the reliability targets, still meeting the power envelopes that subsystem's been designed for, and then really configured with the fastest interface that we have to date for a hard drive, which is the 12 gigabit per second SAS interface. So maybe in conclusion, the storage demand continues to grow. The industry is continuing to demand more and more capacity. We're off developing technologies really for that areal density growth, the hard drive capacity growth in order to meet that demand. I would say that cost is relevant to most of our customers. SSDs would have taken over the world if cost wasn't relevant, but it is. We've got this capacity has to grow at a price point that the market can bear. And then there's a pipeline of technologies here, both in relative to capacity as well as to performance. And we're going to continue to look at this roadmap relative to how we best deploy flash, how we deploy hybrids, and then purpose-built drives, specifically around HPC here, and then perhaps other purpose-built drives as we go forward as well. Thank you.
Okay, we will once again, no Hamburg questions, please. Does anyone like to ask any questions? Please go ahead.
Is the answer.
Minnesotans. Some questions down the end. Maybe we can get the microphone to them. Yeah.
You have to be the back, right? Please go ahead.
Would you use this drive at home to put your pictures on?
Use it at home?
Yeah, in your desktop PC to put your photo collection on it.
There's
How reliable is the disk?
I think the question was, could you use this drive at home?
Of course you can use it at home, but would you use it at home to put your family pictures on the disk? So how reliable is the disk?
How reliable is the disk? So the 2 million hour MTBF spec is the same specification we have for all the nearline drives. So it's compatible and it's the same as all of our business critical 7,200 RPM drives.
So you would use it, let's say, everywhere?
And here's a question there, Ken.
Yeah, I think I'm going to repeat the question. I think essentially the question is, would you use it at home to store your most personal prized family photos?
Oh, yes, I would. But the real question is, would I need to? At a home user, I'm not sure it would bring the same value. This was designed for performance. Very rarely would I end up needing 300 megabytes per second. I do edit some video at home, which is more priceless, but even that has a hard time needing that kind of performance.
Any other questions? Oh, one more.
But while I'm walking down, Dan, I actually have a question myself. So, do we have given we're in the HDD business and we're in the flash SSD business, do we ever see a crossover point in terms of price per gigabytes per second when you think about 3D NAND, et cetera? What are your thoughts on that?
Yeah, we've looked a lot at where the price trends are for flash. I mean, Seagate is an SSD company as well. We do have SSD offerings. Our hybrid drives embed flash as a product of that. And what we've seen is in our cost trends, right? So our cost trends continue to decline on a per terabyte basis, and we don't see any necessarily end to that. So if you look at the industry overall, we're continuing to drive down our pricing. We know that SSDs and flashes are coming down as well, but I think there still will always remain that differential, if you will, on capacity points to price. And certainly if you're needing to save your metadata, which as you start to build these systems larger and larger like this, you're going to have metadata, and you're going to have small block random accesses, and certainly an SSD brings a certain value to those small block random accesses that are orders of magnitude better than a hard drive. And those applications are probably pretty good designed for an SSD. For where you're looking at sequential data rate, where you're trying to do this performance and stream the data, you don't see that differential, and certainly don't see the price getting anywhere close to where a hard drive price is.
Okay, thanks, Dan. Question?
So that was actually sort of my question. I was going to ask, and more bluntly, when do you see all this going away? But maybe more specifically, we're hearing from the flash vendors that they're going after density. We've seen numbers like 20 and 30 terabytes in a little module with low power consumption, but maybe not as much overall performance. So what is the niche that the hard drive occupies, maybe other than HPC? Can you elaborate on that? Or is niche unfair? Is the SSD the niche and the hard drive is still the mainstream storage?
No, and you can see, obviously they'd like to sell you more and more terabytes as with the hard drive guys. A lot of what you see though is you got to ask, are we looking at apples to apples, right? Are they buying, are we able to, fundamentally provide a price point that the hard drive or hard drive based solution, storage solution wouldn't be able to give you? And I think we see our customers broadly based still buying not just the business critical drives, which go into a lot of these high performance compute, but we still see a market for even our 10K and 15K drives, which we know are severely challenged relative to their price per terabyte takedown over time. It's interesting though, we've got folks asking us, can they continue to invest can we continue to invest in 15K products? Those products again are very much go right into the wheelhouse of an SSD. They're small block random devices, and we continue to get asked by our customers, please go develop more of them. So I don't think that the roadmap's over. I don't think that the product line is done. I mean, I think there's a lot of life left in the technologies that we're bringing and the innovation that we bring to this market segment. We got to continue to prove ourselves, don't get me wrong, and that's going to be in making sure we do have that price delta between what an SSD can deliver.
Thanks, Dan. Any other questions? One right here.
Can you elaborate a little bit more on what's really the driving cost behind SSDs and flash storage and why we haven't seen it come down quite as rapidly as one might expect?
Say that again.
Yeah, what's the driving cost behind SSDs and flash storage? So where's all the cost in the manufacture or test or yield of those devices versus a hard drive, and why hasn't the price decreased rapidly?
You're asking me why the SSD price is high.
Oh. I mean, you're a Seagate guy, right?
I've got an opinion, but I think if you look at the cost of what it takes to manufacture an SSD, it's usually pretty simple to find it out, right? There's the flash cost itself, and you can go back and through semiconductor suppliers understand exactly what the cost of a wafer is. You could then look at the yields of that wafer, the yields of new technologies, and how fast they can get up to it. I think fundamentally they got to also amortize the investment they make, right? A new fab is measured in the tens of billions now, right? So it's not cheap. So they've got to amortize that cost away over whatever wafers they can get out of that factory. But beyond that, I mean, I think we can all do the math as to where that cost is coming from. And how they get it taken down is how many bits they ship per wafer. How many bits can they reliably and efficiently and effectively get out of each wafer they ship out of their factory.
Okay, thanks, Dan. I think we'll need to move on to our next presentation.
Okay,
Thanks very much, Dan.
thank you.